Moving on to the practical. This is your working directory. This is your job name. You have to run the screen. After running the screen, you will see this as the interface of the ANSYS. If you want to change the directory, you can go to file. You can go to file, change the job name, change the directory. For now, we have selected a proper directory. Go to plot control, style, color, and reverse video because we want white screen on the background. So you have got the white screen. Now moving on to the preferences. Select which type of problem you want to solve. That is a structural problem. Okay. Then go to preprocessor. In preprocessor, you have to define the element. Go to element, add, edit, define element, add the element. Since we are solving for a structural analysis, we will go with link element. Redefined standard 180 is proper element for us. Don't click on apply, press on OK and close this window. We are going for a single element, and in that single element you have to define real constants. Our real constants, if you see, are three different real constants. Real constants are based on the area. So we have one area, two area, and three area. That means we have three different real constants. So add that three different real constants. So adding on the first link, real constant is 0.001. That is 1000 mm square converted into meter square. Okay, apply करने से set one यहाँ पर create हो जाता है. Set 1 means if you have two area, three area, then you have to go for set number 2, set number 3. Going for set number 2, the area shown to you in set number 2 is 500 mm square, that is 0.0005 meter square. Again apply. We have one more area, that is your set number 3, and that set is having area 300 mm square, that is 0.0003. That is 300 mm square, and 0.0003 is the meter square. So we have three different set. Close this window. We have added three different real constant. Now we need to go for material properties. See, if you can see in the diagram, we have three different materials in this question. So we have to set three different material set as well as we have set for area. So go to material properties, go to material models. Material number 1, we are solving for structural problem, linear, elastic, isotropic. Here you have to input the value of your value of E Young's modulus and bulk modulus. So if you see in your question the value of Young modulus 210 GPa, 12 10 raised to minus 6 per degree Celsius. So going here, you have 210, 210 e raised to 9, that is GPa, and your bulk modulus is fixed, that is 0.3. This we are done with the basic material properties of material. We also want for thermal expansion, so you have to go for thermal expansion and coefficient, thermal expansion coefficient for isometric material, that is being set to us as, we just see what is the value, that is 12 into 10 raised to minus 12 e raised to minus 6. We will check whether it is 12 e raised to minus 6 or not. We'll go to the diagram, just wait. Yeah, 12 10 raised to minus 6 it is. So if you want to see what all you have select, click on this. You can see this value we have selected. Click on this 12 e raised to minus 6 we have selected. Now first material model is selected. Go to material new model. Since our properties of the second material is different, what is the property? Again we need to see the diagram. The property is 100 GPa, 20 10 raised to minus 6. So go to isotropic, 100 e raised to 9, bulk modulus is fixed, click on OK, go to thermal expansion, Sedan coefficient, isotropic, 12 e raised to minus 6 was the one property for previously 12 it was, now it is 20 e raised to minus 6. Okay, it is 20 e raised to minus 6. So let's check. 120, now it is 7524 for the third material. So again new material. Okay, then the properties, it is 75 e raised to 9, 0.3 as the bulk modulus, and Sedan coefficient is 24 e raised to minus 6. Okay, done. So this is all about your constant. We can check what we have selected. So the material properties are set now. The real constants are set. Material properties are set. We will go to modeling section. This section is to be used only when you are using a go to model create. Now we need to create the nodes. So create the node in active sheet. Node number 1. The location is starting point. So we have setting this as the reference point. Then go to active sheet. Material number 2. If you see there in your diagram, you will see material 1, 0, 0 we have set. Then it is at a distance of 100 mm. Second, third is at a distance of 180 mm, and fourth is at a distance of 240 mm. Okay, then we'll go here again in current CS. We have set material node number 1, node number 2 it is 100, that is 0.1 अप्लाई कर देंगे. Then node number 3 it is 0.0.18, that is 180 mm. Okay, now you can see on your screen 3 nodes are appearing. Go on the active CS again. We need 4 nodes. It is at a resistance of 0.24. Okay, so we have plotted the 4 nodes. So we have plotted the 4 nodes. Now we need to go for defining the element. So before connecting the nodes to form an element, define the properties of the element. So go to element attributes. For first element, area 1, material set 1. See, there are 3 areas, 3 material set. For first element, area 1, material set 1. Okay, and then connect the nodes to form element. So we will connect, press on OK. This link is connected as the element from node 1, node 2. Again, set the attribute real constant 2 and material 2. Okay, ये किसके लिए है? सेकेंड एलिमेंट के लिए. सेकेंड एलिमेंट कहाँ है? नोड नंबर 2 नोड नंबर 3 के बीच. Okay, this is again connected. Now if you want to check whether you have connected it properly or not, like you have properly selected the attributes or not, go to list, go to element, attributes and real constant. See, a first area is 1000 e raised to minus 2, second area is 500 e raised to minus 3. So that means we have properly connected it. Then again, element type number 3 and number 3. Okay, and connected node number 3, node number 4, and do it. Okay. Once again, if you want to check, go to list, elements, attributes, real constant, area. Area should change because all the areas are different. So this you are done. Now we have created the nodes, we have defined the element, we have given the properties of area and the material. Now the remaining thing is you need to apply load. So going with the load, just see the diagram. We are solving a problem based on bar under axial load with thermal effect. So in the load column, you have to define the temperature, that is the rise in temperature, and also you have to apply load at module node number 2, node number 3, and you have to fix node number 4 and node number 1. Fixing node number 1 and 4, that means you have to make the displacement at node number 1 and node number 4 as 0. So go to define, analyze, go to define load, go to setting, and set reference temperature. See, your difference in temperature should be 60. So if you set reference temperature as 0, your uniform temperature should be 60, must be 60. If you are defining reference temperature as 20 degree, your uniform temperature can be 80 because the difference should be 60. Like difference in temperature is 60. So that way you can do. Now you are done with the temperature. Go to apply. Go to structural field. First we can select the displacement, or you can apply the force. Go to displacement on nodes. On this node number 1, node number 4, the displacement in all the degree, in all the direction must be 0. Press 0. Okay. So if you can see, let me show you how the diagram basically looks like. See, node number 1 and node number 4 is fixed now. Now it is fixed. Now we need to apply load. Go to structural, go to force on node number 2 we have some load. That load is 49 kilonewton. You can see in this diagram it is 49 kilonewton, 20 kilonewton. But if you see, this is in positive x direction, this is in negative direction. That means the force is tensile over here, and here it is compressive. So select node number 3, press OK, change the value, that is minus kilonewton. So see, the direction is in this direction as per your given diagram. One direction is over here, other direction is over here. Now your problem is ready for getting solved. We have selected the element, defined the area, we have gone for material properties, we have modeled the element, we have applied the load, we are done with the preprocessor. Go to solution, go to solve, current ls you select OK. See, here the solution is done. Close your solution. Now we need to check what are the answers. Go to general post processor, go to result summary, check one by one. You can plot the result. You can plot the result. You can see the deform plus deform shape only. You can see. See, this is just a straight line. Go to plot control, go to style, go to size and shape, displacement of element, on it, click on OK. So this is your deformed shape. If you want to see in 3D, you can see like this. This is your deformed shape. If you want to see deform plus undeformed edges, click on this. This was your previous location of node number 2. Now this is the new location after applying force and change in temperature. This was your old location of node number 3. This is your new location of node number 3. So here in the diagram we can see there is some displacement, but how much displacement we can see from the result list. So if you want to save your result, go to plot control, capture image. This will be directly going into the folder which you have selected. That is the folder which you have selected. This was your folder, experiment number 2. We have selected here. Everything is getting stored as we have selected this, right? So this is getting stored. So now going back to our window. Now see, this is done. Now what we need to do is we need to check the answer. So go to list result. Then you can see nodal load. If you want nodal solution, go to nodal solution, degree of freedom in x direction, how much it is displaced. Press on OK. You will get at node 1 the displacement is 0. At node 2 the displacement is 0.6. At node 3 0.4. At node 4 0. Manually we have solved and we have got the result. Node 2 the displacement is 0.06 mm. Right? Herein it is 0.6 meters. Right? The same answer. 0.6 10 raised to minus 4 meters. The same answer we are getting. This is at node 2. Node 3 0.6 meters. Here it is 0.04 mm. Right? 0.4 and 0.4 into 10 raised to minus 4 meters, and there it is in mm. So that means our solution, what we have manually done, is correct. Now if you want reaction solution, you can go on this all items. Okay, reaction at point number 1, 20 kilonewton minus 49 kilonewton. We will check. This is 20 kilonewton and 49 kilonewton. That means what we have done using the software is giving the correct answer. Now we have also calculated the stress and strain. You can go for that in this also and check with that also if you want. You can go to nodal loads. Go to nodal solution. Wherein you can go to stresses. X component of stresses. You can do this. You will get the answer in x direction, y direction, z direction. That will be similar. That is 0.02 gigapascal. Is 0.2 e raised to minus gigapascal only. So this is your stresses in x direction, y direction. Oh, sorry, in node 1, node 2, node 3, node 4. So this is element 1, element 2, element 3. We are done with this. So now if you want to see how stresses looks in this, you can go to plot, confirm shape, control flow, stresses, do it okay. So these are the values. If you want to see the displacement in x direction, you can click here. These are the displacement. More displacement, maximum displacement is happening in this portion, and then that is displacement. After that, here it is the displacement, and then here it is the displacement. So this is all about the displacement. This is the maximum displacement, 0.6 e raised to minus 4 meters. Okay, so this is all about today.